We will now focus on special angles as we explore trigonometry. So the special angles that we will be thinking about are the angles 30 degrees, 45 degrees, and 60 degrees, which are often found in examples and applications with trigonometry. So they are of special interest. We're going to construct right triangles which contain these special angles, and then understand their associated ratios. So in order to do that, we also need to remember the definitions of our trigonometric functions of acute angles. So for example, we need to make sure we remember that sine of any angle is opposite over hypotenuse. Cosine of any angle looks at adjacent over hypotenuse. Tan of any angle looks at opposite over adjacent. And then we have the reciprocal trigonometric functions. So the reciprocal identities we have is that sine of any angle is equal to 1 divided by cosecant of that angle. And that also means that cosecant of any angle is 1 divided by sine of that angle. And so this will hold true for cosine and its reciprocal trigonometric function secant, and tan and its reciprocal trigonometric function cotan. So now we're going to begin constructing our special triangles. And the first special triangle that we will construct is the 30, 60, 90 degree triangle, but that actually comes from our equilateral triangle, which is the triangle whose 3 angles are each 60 degrees. And if the 3 angles are all the same, then the 3 sides have to be the same as well. So they have what's called a 1:1:1 ratio. Now notice this does not contain a right angle, and we only study right triangles in our course. So what we're going to do is we're going to take this equilateral triangle, and I'm going to choose one of the vertices, and I'm going to drop a perpendicular, thereby creating a 90 degree angle. Now notice I never touched this 60 degree angle, but we bisected this original 60 degree angle, which then creates a 30 degree angle, and there's our 30, 60, 90 degree triangle. Now the other thing that never was touched besides this 60 degree angle is this side right here. So that had an indicator of 1 originally, and because it was never touched, it is still a 1. Now we bisected this angle, which means we also bisected this side. So it is half of whatever it used to be. And we are missing this side right here. Otherwise, we have everything we need to for this triangle. Now for 3 sides of a triangle, if we have a right angle, that makes it a right triangle, and therefore we can use the Pythagorean theorem to solve for that 3rd side. Now we can do so right as we have with the base being 1/2, and now we have a hypotenuse of 1. Or we can recognize that I can actually maintain the ratio of this triangle if I double the base. So double of 1/2 becomes 1, but I need to keep this maintaining all of the other properties of it. So if the base was 1/2 of the hypotenuse, now the hypotenuse has to become 2. So now we're going to solve for this height. So x squared is a leg squared, plus the other leg squared is going to equal the hypotenuse squared. So x squared plus 1 equals 4. And then solving for x squared, we have x squared equals 3. Therefore, x is equal to the square root of 3. Now for right now, we're still looking at acute angles, and so x will only be the positive square root of 3, but in the future we're going to have to make sure we recognize when x will be negative. So now we have a completed triangle in terms of its angles and its sides as they relate to each other for the 30, 60, 90 degree triangle. So we're going to be using this to complete our table below. Now for the next special triangle, this is much more simple to actually create. So we have a 45, 45, 90 degree triangle, which is also known as an isosceles right triangle. Isosceles because two angles are the same. Right because one of the angles is 90 degrees. So one angle is 90 degrees. The other two angles are 45 degrees. And if two angles are the same, that means two sides are the same. And so 45 degrees is across from one leg, and 45 degrees is across from the other leg. So these legs have a ratio of 1 to 1, but we are missing the hypotenuse. So using our Pythagorean theorem, x squared is equal to one leg squared plus the other leg squared. So x squared equals 1 plus 1, x squared equals 2, and so x squared is equal to 2 if x is equal to the square root of 2. So this is the second triangle that we will be using to complete our table below. So now I'm just going to recreate those two triangles to make sure we understand. We have a 30-degree angle, and the side opposite the 30-degree angle is 1/2 of the hypotenuse, and the side opposite the 60-degree angle has a relationship of radical 3, with the side opposite 30 as 1 and the hypotenuse of 2. And then for our isosceles right triangle, we have 1, 1, radical 2. Now for sine, remember sine of any angle is looking at the opposite side compared to the hypotenuse. And we're going to look at all three special angles for sine. So sine of 30 degrees, so my focus is at 30 degrees. And sine looks at opposite over hypotenuse, so sine of 30 degrees is 1/2. Now I'm looking at 45 degrees, and it doesn't matter if I look at this top angle of 45 or the bottom angle of 45. It does not matter as long as I'm using definition of sine of any angle is opposite, which is 1, and hypotenuse is 2. Now notice I left some space there. We've been working on making sure that we always rationalize our denominators, and the square root of 2 needs to be multiplied by the square root of 2 over the square root of 2, which gives us the square root of 2 over the square root of 4, but the square root of 4 is 2. So those are equivalent, and both are very helpful. And then we have 60 degrees, so I'm back over to this triangle, and my focus is on this upper angle. And so sine of 60 degrees, the opposite side is radical 3, and the hypotenuse is 2. Now cosine of our angle is defined as adjacent over hypotenuse. So I need to make sure that I'm looking at the adjacent side as related to my angle and then compare it to my hypotenuse. So for 30 degrees, the side adjacent to 30 degrees is radical 3, but the hypotenuse is still 2. For cosine of 45 degrees, notice that the adjacent side is 1, and the hypotenuse is still radical 2, and rationalized, just as above, is radical 2 over 2. And then finally for cosine 60 degrees, the side adjacent to 60 degrees is 1, and the hypotenuse is 2. And please take a few moments to notice the relationship between sine and cosine. The line for sine reverses for the line of cosine. So that should absolutely be a hint to help you remember how to memorize sine and cosine for these three angles. And then finally for this table we have tan of our angle is defined as opposite over adjacent. And so for 30 degrees, the opposite side is 1. The adjacent side is radical 3. And rationalized, this is radical 3 over 3. For 45 degrees, the opposite side is 1 and the adjacent side is 1. Therefore, the tan of 45 degrees is equal to 1. And for 60 degrees, the opposite side is radical 3 and the adjacent side is 1. So radical 3 over 1 simplifies to be radical 3. Now you have 3 questions here, and all 3 questions actually deal with our special angles. And so the first question is find cosecant of 30 degrees. And so in order to answer this question, we first need to think about what is sine of 30 degrees. Question number 2, determine the exact value of secant of 45 degrees. And in order to answer this question, we first need to think about what cosine of 45 degrees is. And then here, I meant that to be cotan. Determine the exact value of cotan of 60 degrees. And in order to do that, you need to recognize what tan of 60 degrees is.